Hello viewers, welcome back to this course on mathematical finance. This is the second lecture of this module. Remember that in the previous class where we began this topic, we talked about the very important question of pricing of options, and in particular we looked at a model for the underlying asset evolution or the asset price evolution, namely the binomial model. And we looked at a single step model, whereas basically we looked at an initial time t equal to 0, and then we looked at two possible asset price movements from t equal to 0 to time t equal to 1, and had obtained a pricing formulation for this particular option. And we had looked at a little example illustrating how this process ensures that the price should exactly match the value that is required to replicate the eventual payoffs in case of a European call option. So, in today's lecture what we are going to do is that we are going to extend the same concept from a single period model, that is from t equal to 0 to t equal to 1 into a scenario where there are two periods and also three periods, and then extend this and give the option price formulation in case of capital N number of periods. So, we begin our lecture on this topic of multi-period binomial model. So, in this case what we do is that we extend the single period binomial model to multiple periods, and so we do this in the context or the framework of our previous formulation, namely the coin tossing problem. Remember that the coin tossing problem is ideally suited for this binomial framework. And so, here what we do is that we do the coin tossing repeatedly, right, and it results in two possible outcomes, namely a head appears in which case the assumption is that the stock price moves up by a factor. Remember, we had the up factor of u, and secondly a tail appears, and in this case the stock price goes down by a factor of d. So, now what I want to point out here is that what I am saying is that earlier we started off with the initial stock price at S naught, and we said that what the prediction regarding the stock price at time t equal to 1 as a random variable will be driven by a coin tossing problem, wherein there are just two possible outcomes, namely a head and a tail. And we had assumed that in the event that there is a head, then the stock price will go up by a factor of u. That means, it will go from S naught to u into S naught, and in the event of a tail, it is going to go down from S naught to d of S naught. Now, when we are going to extend this in case of a multi-period model, the assumption is that we will repeatedly do the coin tossing problem. So, if you have three number of periods that you are likely to we are going to consider, in that case we will have to toss the coin consecutively 3 times, and depending on each of those coin tossing whether a head or a tail comes, we model it by a upward or a downward movement accordingly. So, this in general will be extended to a n period model, where you essentially have to do n number of tosses, and for each toss a head will indicate that there is a upward movement from the present time period to the subsequent time period, and in case of a tail there is going to be a downward movement of the stock price from the present stock price to the stock price as a random variable in the next time point. Okay, so also another assumption here we make is that the up factor and down factor, it will be taken as a constant across the entire all the periods. That means, as you move from t equal to 0 to 1, t equal to 1 to t equal to 2 and so on. In each of those time periods, the assumption is that the up factor u and d are going to be constant every time. Further, we assume that the constant interest rate for a single period is r as before. The other assumption is the one due to no arbitrage. So, it is that the no arbitrage condition is satisfied. So, recall that what is the no arbitrage condition? It was that d is strictly less than u, and 1 plus r is basically sandwiched between these two values. Okay, now what we are going to do now is actually look at the model setup. So, accordingly, let the stock price at the initial time point t equal to 0 be a positive number s naught as before. The price at the end of the first period of the binomial model, namely that time t equal to 1, is denoted, and this is a random variable. So, as before, we will denote this by S1 of h, which was u of S naught, if the first toss was a head, and secondly, S1 of t is equal to d S naught if the first toss was a tail. So, this is basically exactly the same setup that we had in case of the single period model. Now, after the second toss, what is going to happen? What are going to be the possible prices? So, the price will be one of the following. Firstly, so let us look at, so there are 4 cases that will actually come out of it. First of all, we will have the case, suppose that the first toss was a head. In this case, then it will be either followed by another head or tail, and if the first toss was a tail, it will also be either followed by a head or a tail. So, this is the complete exhaustive list. So, the price S2, so there are 4 possible values of S2 depending on the sequence of outcomes of 2 coin tosses. Now, S2HH is what? S2HH is nothing but the fact that you had an upper movement of a factor of a from S1. So, you start off with S naught, and this is S1 of h, and this is S1 of t. So, S2 of HH so S2 of HH that you are considering here is a result of an upward movement from S1 of h. So, I have written this as u of S1 of h, and you know that S1 of h is u of S0. So, this simply becomes u into u S0, which is equal to u square S0. Also this sort of follows obviously because it is 2 heads. So, 2 heads means 2 upward movements from the initial price of S naught. So, you can straight away see that this is u square into S naught. Likewise, S2 of HT here was is basically a movement of downward movement which is followed from S1 of H. So, you had a S1 of H and you made a downward movement to arrive at S2 of HT. So, this is going to be equal to d into S1 of H, which is d into u of S naught. So, likewise this is going to be nothing but u into S1 of t, and this is going to be d into S1 of t. Remember S1 of t is d S naught. So, this will become u d into S naught, and this will simply become d square into S naught. Now, let us look at the case of the third period, namely what happens between time t equal to 0 and time t equal to 3. So, after 3 tosses, this, how many outcomes you will get? You will basically get 8 outcomes of coin tosses, which means that you will get 8 possible values of the stock price, not necessarily all distinct. So, what do you have? If you have now at the end of the second toss, you had 4 possibilities: head head, head tail, tail head and tail tail. Now, each of those possibilities results in 2 possibilities, new possibilities. So, you will have a head head followed by a head head followed by a tail tail followed by a head tail followed by a tail head followed by an head head followed by a tail tail followed by a head and tail followed by tail. So, this is the complete and exhaustive list of all possible sequence of coin tosses when you have tossed the coin 3 times. So, depending on each of the circumstances, what is going to be the stock price S3 under each of those circumstances. So, let us articulate each of those cases one by one. So, when there are 3 heads, that means there has been 3 upward movements. So, this is going to be u into u into u, which is u cube S naught. In this case, there are 2 heads and 1 tail. So, it is going to be u square d into S naught. In this case also there are 2 heads and 1 tail. So, it is u square d into S naught. In this case, the HTT, there are going to be 2 tails. So, it is or 1 head. So, it is u d square S naught. In case of THH, again there are 2 heads. So, it is going to be u square d S naught. For THT, it is 1 head. So, I get a u and 2 tails. So, I get d square into S naught. For 2 tails and 1 head, I will again get u d square S naught, and the case of all tails, I will basically get d cube S naught. So, you see that u cube S naught is one value, d cube S naught is another value, and u square d S naught, there are 3 cases, one here and one here. And similarly, there are 3 cases of u d square S naught. So, one I have here, one here and one value is here. So, we can put this in the form of a tree. So, we start off with S naught. We have S1 of H, which is equal to u S naught. We have S1 of T, which is d S naught. From here we get S2 of HH, which is u square S naught. From here we get S2 of HT, which is going to be the same as S2 of TH, namely u d S naught, and from here we arrive at S2 of TT, which is d square S naught. So, likewise from here we will get S3HHH, which is U cube S naught, okay. And likewise we will get S2 S3 HHT, which is U square D S naught, and likewise you can generate the entire tree based on whatever observations we have made here. Alright, so now let us see how we are actually going to extend this and how does it actually work. So, our goal, eventual goal is to extend this in case of a n greater than or equal to 2 time period binomial model to price an option. Remember, now that we have explained the how the tree is actually generated and how naturally it can be extended to capital N number of time periods, we can now start expanding the fundamental principle of the risk neutral pricing that you had done in case of a one period model by making use of replication, and the next goal is to extend this replication strategy in case of a 2 period model and then obviously naturally to a n period model. So, let us look at the case of n equal to 2. Remember, we had done the option pricing for n equal to 1. So, accordingly we look at the payoff at time t equal to 2 is given by say V 2. So, V 2 is going to be equal to S 2 minus k plus for a European call. Now, note that here both S 2 and V 2, right. Remember, S 2 had two components. S 2, as you remember, S 2 was something that is dependent on both the first two coin tosses and the sequence in which they appear, and more importantly the number of heads and tails that come. So, obviously, S 2 is dependent on what is the outcome of the first two coin tosses, and likewise and obviously consequently, because if you are just considering the value of a derivative in a 2 period model which will be dependent on S 2. So, obviously, if S 2 is dependent on the first two coin tosses, naturally V 2 is also going to be dependent on the first two the outcomes of the first two coin tosses. So, both S 2 and V 2 are dependent both on the first and second coin tosses outcome. So, the immediate question that arises is what is going to be the no arbitrage price of the option at time t is equal to 0. Please bear in mind that whenever you are talking about the price of an option, it is customary to refer to it as the price that the buyer of the option pays at time t equal to 0, and subsequently when you talk about the evolution of the price of the option over a period of time, then it will be specified that it is the price of the option at that particular intermediate time period, but unless otherwise stated, the price of an option will always mean that what is the price of the option at time t equal to 0 when the option was initiated. So, in the mathematical formulation, this basically means that we need V naught needs to be determined. So, the idea is the following, is that the writer gets V naught and buys delta naught, just like we had done in case of the single period model, buys delta naught shares, delta naught yet to be determined, of the stock for a total amount of delta naught S naught, and invests the balance. What is going to be the balance? The balance is going to be V naught minus delta naught S naught at rate R. And of course, if this turns out to be negative, so it will mean that you have to borrow if V naught minus delta naught S naught is negative, just as we had seen in the numerical example that we saw in the last class. Now, what happens at time t equal to 1? So, the argument of what happens at time t equal to 1 will follow more or less on the lines of what we have already done in the single period model. So, at time t equal to 1, the position of the portfolio, what was the portfolio? Delta naught shares and the remaining amount in a risk free account. So, the position of the portfolio of the writer is valued at, so you had delta naught shares which now has a value of S1. So, the total value is delta naught S1 plus the remaining amount of V naught minus delta naught S naught has now grown to by a factor of 1 plus R. And this is a random variable because x1 is a random variable and this is going to be equal to x1. Now, since S1 and obviously consequently x1 are both dependent on the outcome of the first coin toss. So, we obviously get two values for x1, exactly the same we had done in case of a single period model, where x1 is basically a random variable, and what I am saying is by what I mean by two values for x1, it means that it is a random variable which takes two values of x1. So, what are these two values? This is contingent on the outcome of the first coin toss, which could either be head or it could be tail. So, accordingly, the values of x1 under these two possible outcomes of coin toss is going to be delta naught into S1 of h in the first case plus 1 plus R, V naught minus delta naught S naught, and delta naught S1 of t plus 1 plus R into V naught minus delta naught S naught. So, I call this set of two equation as equations 1. Now, we have the complete setup of what has happened at time t equal to 1. Now, at time t equal to 1, the portfolio, what was the portfolio? Delta naught share and the remaining in a risk free account. So, this portfolio is valued at x1 and can now be readjusted. This means that I can actually reshuffle the number of units of the stock and what proportion of money I put in the risk free account. So, accordingly, so now the writer, what he or she will do is the following, that the writer decides to hold delta 1 shares of stock. So, remember that at time t equal to 0, the number of shares that was purchased was delta naught, and once you arrive at time t equal to 1, then the portfolio can be reshuffled and the number of shareholdings can now be changed from delta naught to delta 1. So, the writer now decides that he or she wants to have delta 1 shares of stock, and so this is allowed and this is what something that depends on the first coin toss, right. So, the decision of delta 1, which is yet to be ascertained, will depend on what has happened in the first coin toss. So, there will be one delta 1 value, it will be ascertained if the first coin toss was a head, and in case the first coin toss was a tail, the strategy in terms of number of shares that you own, that is delta 1, is going to be something different, or is likely to be something different. So, since this depends on the first coin toss, because another reason we talk about that this dependency is because the outcome of the first coin toss is known at the time of choosing delta 1. So, this is strongly related to a concept called filtration that you will see later in the course, where basically a decision is being made at a time point, intermediate time point, which is, and one of the drivers of the decision is that all the information as far as the movement of the asset price is concerned up to that particular point is known when you are making the decision. So, in this case what has happened is that when you are sitting at time t equal to 1, by that time you know whether a head and or a tail has taken place. So, suppose that a head has taken place. So, you obviously know that at time t equal to 3 you cannot have an outcome where there are 3 tails. So, that is ruled out. So, this is what is known as basically the information is passing, or in the parlance of stochastic calculus, this is what is known as a filtration. All right. So, what happens is that once you have sorted out this x 1 and delta 1, what you do is that in that case once you have invested delta 1, so what is the remainder? So, the remainder is going to be, you had an amount of x 1 which is of course dependent on head or tail, and you have invested delta 1 into S 1 in the shares, and the remaining amount, this remaining amount that you have, which is x 1 minus delta 1 S 1, where each of these is basically going to be dependent on the first coin toss, is invested at a rate small r. So, at time t is equal to 2, what will we have? At time t equal to 2, you had delta 1 shares we bought at time t 1. So, its value at time t equal to t equal to 2 is going to be delta 1 into S 2, plus you had invested this amount at rate r. So, this will now become x 1 minus delta 1 S into 1 plus r, and this must match the value V 2 at time t equal to 2. Now, obviously, we can make an observation here that S 2, which is the price of the stock after 2 coin tosses, is obviously dependent on the outcome of the first 2 coin tosses, and so obviously V 2 will also depend on the outcome of the first 2 coin tosses. Okay, so this results in what? This results in 4 possible outcomes. So, this is good. This is good news. So, what are the 4 possible outcomes? Remember, the 4 possible outcomes was head head, head tail, tail head, and tail tail. So, accordingly, I will have 4 values of V 2, V 2 HH, V 2 HT, V 2 TH, and V 2 TT. And this is going to be delta 1. Now, remember, in the first case, what is going to be the delta 1 a function of? See, in this case and this case, the head appears first in the first toss. So, delta 1 decision was made with the information available that a head has happened in the first coin toss. In the third and the fourth case, there was a tail in the first coin toss. So, accordingly for these two scenarios, the delta 1 will depend on tail, which was the first outcome. Then this will be multiplied by S2 obviously of HH, same as HH here. This will be second case, it will be S2 of HT. In the third case, it will be S2 of TH, and the fourth case, it will be S2 of TT. And now we look at this term is done, and we look at this particular term. So, this particular term will get x1. So, we will have a factor of 1 plus r that is common for all the cases. And also here, so in this case, we will have x1. Remember, x1 depends on the first coin toss, which was head. So, this is going to be x1 of h and x1 of h. And here for the third and the fourth case, x1 will depend on t and t, minus of course delta 1 of h and delta 1 of h for the first two cases, and delta 1 of t for the third and the fourth cases, multiplied by S1. So, again S1 is something that is dependent only on the first coin toss. So, it is going to be S1 of h, S1 of h, S1 of t and S1 of t. So, I call this set of equation to be equation 2. So, remember what was equation 1? Equation 1 was basically the portfolio valuation at the end of time t equal to 1. So, this is one set of equation, and this is the second set of equation. Equation 2 is the portfolio values which must match V2 in all cases at time t equal to 2. So, in equation 1 we had 2 equations, and in equation 2 we had 4 equations. So, these two sets give total of 6 equations. So, in 1 and 2 we thus have 6 equations. And what are the unknowns? So, there are 6 unknowns that are accompanying it. What are these unknowns? These unknowns are basically delta 1 of h, delta 1 of t and delta naught to be ascertained. You need to ascertain what your V naught is, and you want to know what is x1 of h and x1 of t. Alright, so now solving this set of equations, we can actually obtain delta 1 of t to be equal to V2 of th minus V2 of tt divided by S2 of th minus S2 of tt. And this will imply that x1 of t is going to be 1 over 1 plus r multiplied by the p tilde V2 of ht, rather V2 of th plus q tilde into V2 of tt. And this is nothing but this is going to be same as V1 of t. Likewise, we can obtain, so likewise we can obtain delta 1 of h to be equal to V2 of hh minus V2 of ht divided by S2 of hh minus S2 of tt, and x1 of h, which is V1 of h, is going to be 1 over 1 plus r into p tilde V2 of hh plus q tilde V2 of ht. So, you observe very carefully how we actually got it. So, here delta 1 of t is nothing but change in the value of V2 divided by change in the value of S2. So, this means that the outcome from, so the first you had started off with S naught, and then you actually go up to S1 of h or down to S1 of t. Now, when I am saying that I want to ascertain my delta 1 of t, that means that this event has not happened, but this has happened. So, in this case, this leads us to two values of s, namely S2 of th and S2 of tt. So, the denominator is going to be the difference of S2 of th minus S2 of tt, and the numerator is going to be the corresponding difference of the values for the same outcome in that order. Now, further, in this case, the value is going to be V2 of th if there is an upward movement from time 1 to 2, and this is going to be of V2 of tt. So, the value of V1 of t is going to be the expected discounted value of V2 of th and V2 of tt. So, accordingly, we have V2 of th and V2 of tt multiplied by the corresponding risk neutral probabilities p tilde and q tilde, and then discounted by 1 plus r, and this is going to be V1 of t at time t equal to 1. All right. In a similar fashion, you can have exactly the same argument in the second case, where you again start off with S0, you go to S1 of h and S1 of down to S1 of t. Now, since you are considering the case of delta 1 of h, that means this event is ruled out and you should consider S1 of h. Now, from S1 of h, your value of the stock can go up to S2 of hh, or it can come down to S2 of ht. Okay. So, this actually should be S2 of ht. So, as before, you see the denominator is nothing but the difference of S2 of hh minus S2 of ht, and the numerator is V2 of hh minus V2 of ht. So, it is a corresponding difference that you see in the denominator, and what is going to be the value V1 of h. The value V1 of h will be the discounted value of the expected value of V2 of hh and V2 of ht. So, what do I get? I get V2 of hh, V2 of ht. I multiply it by the corresponding risk neutral probabilities p tilde and q tilde, and I discount it by a factor of 1 plus r. So, by looking at this the binomial tree, you are actually able to ascertain what is delta 1 for both the circumstances. The two possible delta 1 values at time t equal to 1 are resulting in the corresponding V1 values at time t equal to 1. Now, we are going to use the same tree kind of an argument that we have used in these two cases to find out what is the value of the option V0 at time t equal to 0, which was the first question that we sought out to answer. What you can have now, so then we have delta naught and V naught, which you can actually obtain by solving the equations, which you have already done in the previous class. So, remember that delta naught is V1 of h minus V1 of t divided by S1 of h minus S1 of t, and V naught is going to be 1 divided by 1 plus r into p tilde V1 of h plus q tilde V1 of t. So, remember in the previous step we had actually figured out what is going to be V1 of h. So, this should be x1 of h. So, V1 of t and V1 of h. So, this information is available. So, now we again view this binomial tree. So, for S naught you can go up to S1 of h, or you can come down to S1 of t. So, the denominator is nothing but the denominator in case of delta naught is nothing but the difference of the s values, and the numerator is the difference of the corresponding v values, namely V1 of h and V1 of t. So, what you do is that now you want to find out what is V naught. So, V naught is going to be the discounted value of the expected values. So, one value that you can attain at time t equal to 1 is V1 of h, with probability p tilde, and the other value that you can obtain is v 1 of t with probability q tilde. So, this will give the expected value of v 1 discounted by 1 plus r in exactly the same manner that we had done in the case of figuring out what is v 1 of t and v 1 of h. And this is again the same formula that you had obtained in case of the single period binomial model. Now, summarizing, we have three stochastic processes, namely delta naught and delta 1. So, the evolution of deltas, then the evolution of x, x naught, x 1, x 2, that means the evolution of the replicating portfolio, and correspondingly the evolution of v naught, v 1 and v 2. And note that, so where a stochastic process is a sequence of random variables with time indexing. Okay, so now let us see how we are actually going to extend this in a generalized case. So, in general, the value of a portfolio of, which is the portfolio? The portfolio, as before, it is a portfolio of holding a number of stocks, namely delta naught, delta 1 and so on, that you have seen previously. So, number of stocks and then borrowing or investing depending on whether the remaining amount that you have after the investment in stocks, whether it is positive or negative. So, borrowing and investing at say rate r from an initial amount x naught is represented by, so you, for this you actually consider that this time point n and n plus 1. So, you can write this as at n you buy delta n number of shares, all right, and then the remaining amount. So, at time n you have an amount of x n, out of which we had spent an amount of delta n s n in buying the stock, and so you invest this at rate r and you buy delta n stocks. So, its valuation at time n plus 1 will be the value of the stocks, price of each stock s n plus 1 multiplied by the delta number of stocks you had purchased, plus the amount of x n minus delta n s n that was invested at rate r, which has now grown to by a factor of 1 plus r, where x n and delta n are chosen for replication. And correspondingly the v n that you have, this is going to be the price of the derivative security, which in our case for most part will be treated as option. Now, what you can do is that using the patterns or observations, we now can state the following, and I will state this particular theorem. So, here goes the theorem. So, this theorem is about replication in a multi-period binomial model. So, what you are going to do is that the way we do the pricing, and we have seen the pricing being done in case of one time period in the last class and for the two time period in the present class. We are basically going to extend this idea in a generalized case where there are n number of periods where this n, or rather capital N, is going to be greater than 2. So, then we consider an n period. So, the way this is stated now, of course, is also applicable for n equal to 1 and 2, which we have looked at separately. So, we consider the n period binomial model with parameters d, u and r satisfying this no arbitrage condition, and with p tilde as already defined being 1 plus r minus d divided by u minus d, and q tilde you would recall is defined as u minus 1 plus r divided by u minus d. So, now let v n be a random variable. So, this is a derivative security payoff at time n, and this V n depends on the first n coin tosses, and we will denote this n coin tosses as omega 1, omega 2 all the way to omega n, where each of those omegas can either be a head or a tail. So, basically this particular notation indicates capital N number of consecutive outcomes of coin tosses. So, it is basically a sequence of capital of length capital N, which can either be where each of those characters can actually be either head or a tail. So, in case n equal to 1, you just have omega 1, which is h or t. In case of n equal to 2, you will have omega 1, omega 2, where there are 4 cases, namely hh, ht, th and tt. So, then we will define recursively backward in time the sequence of random variables v n minus 1, v n minus 2 all the way to v naught by, so we will define it in the usual fashion. So, what you do is the following, we will look at 2 time points. So, I will just explain this on the side. We will look at 2 time points n and n plus 1. So, this means that at time n you already have a sequence omega 1 to omega n, and at time n plus 1 the sequence will either be omega 1 to omega n head. Remember, this is the filtration that is available, and this is either we are going to go up because of a head, or in the second case when you go down because of a tail, it is going to be omega 1, omega 2 all the omega n all the way to t. So, this means that I will look at the value at n plus 1 for omega 1 all the way to omega n into h. This is one value here, and v n plus 1 in this case is going to be v n plus 1 omega 1 to omega n t. And what is going to be the expected value of this? If this happening has a probability p tilde and this happening has a probability of q tilde. So, the expected value will be sum of this, and I will discount this by a factor of 1 plus r. And what is this going to give me? This is going to give me the value at v at which was a consequence of small n number of coin tosses. So, I define the sequence of random variables v n minus 1, v n minus 2 all the way v 0 in this particular fashion. So, because you remember that Vn you already know it is simply going to be the payoff of the derivative, and you use Vn to calculate Vn minus 1 from this particular formula. And then once you have obtained Vn minus 1 by replacing n to be equal to n minus 1, you can then use this in case of n minus 2 to find Vn minus 2 and so on until you arrive at time v is equal to 0. So, only Vn can be calculated by looking at the final possible values of the asset price and the consequent payoff, and all subsequent intermediate values all the way up to the initial value of the derivative, or in particular if you want to view it as an option, can be figured out by making use of this recursive relation. So, this particular recursion we have already seen specific cases of it earlier when you were calculating V1 and V0 from V2. So, the continuing with the statement of the theorem. So, we define recursively this sequence of random variables. So, once I have defined this Vn minus 1 all the way to V0, so that each Vn depends on the first n coin tosses, namely this omega 1 all the way to omega n, right, where of course your n could be capital N minus 1, n minus 2 all the way to 0. So, next we define delta n of omega 1 to omega n. So, delta n is the strategy that you actually adopt here and which you hold on to until this final time point. So, remember what is this? This is going to be the difference of the price of the asset for this minus this. So, this can be written as S n plus 1 of omega 1 all the way to omega n into head minus S n plus 1 omega 1 all the way to omega n into tail, and the numerator will going to be exactly the same thing, that is omega 1 through omega n head and tail, but the valuation for Vn plus 1. So, you have now defined what is Vn and also you have defined what is going to be your delta n. All right. So, where of course, your n is going to be equal to n minus 1, n minus 2 all the way to 0. Now, if we set x 0 is equal to v 0 and define the value of portfolio that is x 1 all the way to x n by the relation x n plus 1, which you have already seen, x n plus 1. Remember, this is just the same relation as we had seen here, exactly this same relation. So, I am just reproducing it. So, x n plus 1 is equal to delta n s n plus 1 plus 1 plus r into x n minus delta n s n. Then we will have x n omega 1 all the way to omega n to be equal to V n omega 1 all the way to omega n. All right. So, what it means is the following. So, just to see the things in context, consider a binomial n period binomial model which satisfies this no arbitrage condition with the following defined risk neutral probabilities, and if I define the values of V n in this manner, starting off with V capital N as the payoff of the derivative, and if we define the delta n to be this, then a process where I start off with x 0 is equal to V 0 as already defined, and then all the subsequent x n's are defined by making use of the delta n's which I have defined here. So, remember I first figured out what is going to be my Vn, I then use my Vn to get my delta n, right. I need these Vn values, and once I get delta n, I can use this to define my xn plus 1. So, these xn's that I have here will match all the values of Vn. So, basically this is the theorem which talks about the replication. That means, your replicating value of the replicating portfolio xn will always be matching Vn if you define Vn and delta n as specified earlier in the theorem. So, this does two things. What it does is that it gives you the replication strategy and that it actually works, and secondly also it gives you a formula for valuation of the option price. So, just to sum up whatever we have discussed today, we mainly looked at two things. We looked at a 2-period binomial model and a 3-period binomial model, and we sort of extended the one pricing of a derivative or an option in case of the 1-period model to the 2-period model, and observing the pattern we went ahead and looked at this last theorem which gives us the valuation at any given time from 0 to n minus 1 resulting in the consequent values of delta, which is used to design a replicating portfolio such that the value of the replicating portfolio at every time point without any exception must be matching the value of the derivative at all those time points. So, in the next class we will continue a little more on this binomial model and option pricing, and that will conclude this first part of this discussion on option pricing in the binomial setup. Thank you for watching.